Welcome to Ultimate Sleep Doctor. Tonight, we journey to a place of quiet wonder. Across the vastness of space, a red planet beckons. Mars, a world sculpted by ancient mysteries and the echoes of a distant past. Scientists tirelessly send probes and rovers to unlock its secrets, to understand its geological formations, search for signs of water, and ponder the possibility of life beyond Earth. There's a beautiful stillness in this pursuit, a reminder that even the grandest explorations begin with a single, curious step. Let your mind settle, finding peace in the knowledge that the universe holds endless possibilities. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. The search for life beyond Earth has always been a grand, patient quest. We've looked to distant moons, swirling nebulae, and the cold vastness of space. But for a long time, our gaze kept returning to Mars. There's something about the red planet, its rusty hue and familiar size, that sparks a deep curiosity. But finding life on Mars isn't about simply landing a rover and hoping for a surprise. It's about understanding the planet's past, particularly a time when it might have been much warmer and wetter than it is today. And a key piece of that puzzle lies in the search for ancient Martian lakes. Scientists believe that early Mars, billions of years ago, was vastly different. The planet possessed a thicker atmosphere, trapping more heat from the sun. This warmer climate could have allowed for the existence of liquid water, a crucial ingredient for life as we know it. However, Mars is now a cold, dry world, sculpted by winds and dominated by a thin atmosphere. The evidence for past water is abundant: dried riverbeds, sedimentary rocks, and minerals that form only in the presence of water. But the most compelling evidence comes from the potential remnants of ancient lakes. The Curiosity rover, currently exploring Gale Crater, has been playing a particularly important role in this search. Gale Crater is believed to have once housed a large lake, formed when a massive impact created a depression in the Martian surface. The lake wasn't just a puddle, it was a substantial body of water, perhaps several kilometers across. As the lake filled, it deposited layers of sediment, mud, sand, and clay, much like rivers and streams on Earth deposit material as they flow. These layers form sedimentary rocks, and within these rocks, scientists are looking for traces of past microbial life. The key is understanding how these sediments formed and what they might contain. Curiosity has been meticulously examining the layers of Mount Sharp, a towering peak at the center of Gale Crater. The mountain's layers represent a record of the lake's changing history. Lower layers, closer to the crater floor, are thought to represent an older, deeper lake, while higher layers correspond to a younger, shallower lake. Each layer holds a potential story about the conditions that existed at the time it was deposited. Curiosity utilizes a suite of instruments to analyze these rocks. The rover's Mastcam, a pair of orbiting cameras, captures high-resolution images, allowing scientists to study the texture and structure of the rocks. The ChemCam laser, a powerful beam of light, analyzes the chemical composition of rock samples, identifying minerals and elements. Perhaps most importantly, Curiosity carries the sample analysis at Mars SAM instrument suite. SAM is designed to heat tiny samples of rock and soil, releasing gases that can be analyzed to determine the presence of organic molecules, the building blocks of life. The search isn't just about finding organic molecules, it's about finding evidence of their origin. Did these molecules form through biological processes, or did they arise from non-biological reactions, like volcanic activity? Scientists are looking for specific patterns in the organic molecules, like the presence of certain isotopes, variations of elements with different numbers of neutrons. Biological processes often produce a distinct isotopic signature, a bias towards lighter elements. Detecting this bias would be a strong indication that life was once present. Beyond Curiosity, the Perseverance rover is currently exploring Jezero Crater, another area believed to have once hosted a lake. Jezero Crater is particularly exciting because it contains evidence of an ancient river delta, where a river flowed into the lake. This delta could have provided a concentrated source of nutrients and water, potentially creating a thriving ecosystem. Perseverance carries a sophisticated caching system, collecting carefully selected rock samples for eventual return to Earth. These samples, once analyzed in Earth-based laboratories with far more advanced equipment, could unlock even more secrets about ancient Mars. The search for life on Mars is a slow, deliberate process. It requires patience, meticulous observation, and a willingness to interpret ambiguous data. The Martian environment is challenging, and the evidence of past life, if it exists, is likely to be incredibly faint. However, the potential reward, the discovery that we are not alone in the universe, is immense. Scientists are also investigating other potential environments where life might have thrived on Mars, such as hydrothermal systems, areas where hot, mineral-rich water flows beneath the surface. These systems could have provided a stable, energy-rich environment for microbes. Detecting biosignatures in these environments, which could be shielded from the harsh surface conditions, is a significant area of focus. The idea of subsurface life is particularly compelling. Mars' surface is bombarded with radiation, and the soil is heavily oxidized, meaning it's rich in iron oxides, which give the planet its red color. This makes the surface a hostile environment for life. However, beneath the surface, shielded from radiation and with potentially warmer temperatures, conditions might have been more favorable. Ultimately, the search for life on Mars is a quest to understand our own origins. By studying another planet's history, we can gain a better understanding of the conditions that allowed life to arise on Earth. It's a humbling endeavor, reminding us of our place in the vast cosmos. The journey to answer the profound question of whether life exists, or once existed, beyond our planet is just beginning, and with each new discovery, we move closer to unlocking one of the greatest mysteries in science. The data coming back from Mars is slowly painting a picture of a planet that was once far more vibrant and dynamic than it is today. It's a story of transformation, of a world that shifted from a warm, wet environment to a cold, dry one. But within that story lies the possibility, the hope, That ancient life may have endured, quietly hidden within the rocks, waiting to be discovered. The Perseverance rover, a remarkable machine built for a very specific purpose, has been diligently exploring Jezero crater on Mars, and its mission isn't just about looking around. It's about collecting tiny, precious pieces of Martian history, rocks and soil, that scientists back on Earth can study with incredible detail. Perseverance's central task is the sample collection system, a sophisticated and remarkably delicate piece of equipment designed to find and retrieve the most promising geological materials for future return to our planet. This system isn't a simple scoop and grab operation. It's a carefully orchestrated series of steps intended to ensure the integrity of the samples and maximize their scientific value. The core of the system is the coring drill, a marvel of engineering. It's a rotating percussion drill, meaning it spins and then taps repeatedly into the Martian surface. This is necessary because the type of rocks Perseverance is looking for, specifically sedimentary rocks, are often layered and cemented together. A regular scoop would simply break them up and mix the fragments, making it impossible to analyze them properly. The coring drill, however, can penetrate up to 5 feet, 1.5 meters into the ground, collecting cylindrical rock samples about the diameter of a pencil and several inches long. These cores are incredibly valuable because sedimentary rocks, formed from the accumulation of sediments like sand, mud, and clay, are particularly good at preserving evidence of past environments. Think of ancient riverbeds, lakes, or even hydrothermal systems. Once the coring drill has extracted a core, Perseverance immediately moves into a system of robotic arms and brushes. These arms carefully clean the exterior of the core, removing any loose dust or debris. This is crucial because even tiny particles of Martian dust could contaminate the sample and skew the results of analyses performed back on Earth. The rover then uses a series of brushes, similar to those used on Earth to clean delicate scientific instruments, to gently scrub the surface, revealing the rock's true texture and composition. The rover's Mastcam-Z, a pair of high-resolution cameras, meticulously documents the core's appearance, the color, the layering, any fractures or grains visible to the naked eye. This detailed visual record is invaluable for scientists to understand the context of the sample and plan future investigations. Perseverance isn't just collecting cores, it's also gathering samples from the surrounding soil using a technique called rock rolling. The rover uses a rocker wheel suspension system, allowing it to move back and forth in a controlled manner. As it rocks, it picks up and brushes loose sediment, the powder, from the ground. This powder is then collected in a sample tube, designed to seal tightly, preventing contamination and preserving volatile compounds like methane, which could indicate past biological activity. The powder samples are especially important because they can provide information about the environment in which the sediment was deposited. Scientists believe these lighter-weight materials might offer a different perspective on the region's past. The scientific goals behind this sample collection system are exceptionally ambitious. Perseverance is searching for evidence of past microbial life, But it's not simply looking for fossils, although those would be an incredible discovery. Instead, the rover is investigating potential biosignatures, chemical or mineralogical traces that could indicate that life once existed. These biosignatures could include specific types of clays that formed in the presence of water and microorganisms, or the presence of organic molecules, the building blocks of life. The rover is equipped with a suite of instruments to detect these biosignatures, including the SHERLOC instrument, which uses ultraviolet lasers to identify organic compounds, and the PIXL instrument, which creates a detailed chemical map of the sample's surfaces. Furthermore, the samples are intended to provide a detailed record of the environmental conditions that existed in Jezero crater billions of years ago. By analyzing the composition of the rocks and soil, scientists can reconstruct the climate, the water cycle, and the geology of the region. This information can help us understand how Mars evolved over time and whether it ever had the potential to support life. The samples aren't just about finding microbes. They're about understanding the conditions that made Mars habitable, or not. Scientists are particularly interested in studying ancient lake beds and river channels, which are known to have provided favorable environments for life to emerge. Perseverance is programmed to select the most scientifically valuable samples, those that are most likely to contain preserved biosignatures or provide the best record of the past. It does this by carefully observing the geology of the area, using its cameras and instruments to assess the quality and potential of each sample. The rover prioritizes samples from areas with evidence of ancient water activity, such as sedimentary rocks and altered minerals. It's also collecting samples from a diverse range of geological settings to ensure that the returned sample represent the full range of possibilities on Mars. A crucial element of the mission is the capsule, a small, robust container designed to protect the samples during their journey back to Earth. After Perseverance collects a sample, it carefully seals it inside the capsule, along with a backup capsule. This ensures that the samples remain pristine until they are retrieved by the Mars Sample Return Campaign, a joint effort between NASA and the European Space Agency. These samples will then be transported back to Earth for detailed analysis in state-of-the-art laboratories, labs where scientists can use instruments far more powerful than those carried on the rover itself. Ultimately, the Perseverance rover's sample collection system is a testament to human ingenuity and our relentless curiosity about the universe. It's a sophisticated machine designed to unlock the secrets of Mars, and the samples it collects may hold the key to answering one of humanity's greatest questions. Were we ever alone in the universe? The careful planning, the intricate technology, and the ambitious scientific goals all point to a future where we can learn much more about Mars, and perhaps about our place in the cosmos. The journey to Mars wasn't solely about scanning the surface for ancient rivers or meticulously gathering rocks. There was another, incredibly ambitious project woven into the fabric of the Perseverance mission: ingenuity. It wasn't a grand, sweeping probe designed to map continents, but a tiny, remarkably brave aircraft. the first ever to attempt powered flight on another planet. Ingenuity, short for Ingenuity Technology Demonstrator, was a helicopter conceived as a high-risk, high-reward experiment to prove that controlled flight was possible beneath the thin atmosphere of Mars. The team at JPL, Jet Propulsion Laboratory, hadn't intended for Ingenuity to be a primary scientific instrument. Its initial purpose was simply to provide reconnaissance, a quick, close-up look at the landing site, acting as a scout for Perseverance. They needed to know precisely what they were driving over, assess the terrain hazards, and confirm the accuracy of the landing. The design of Ingenuity was deceptively simple. It was roughly the size of a small drone, about 1.6 meters tall, and with a rotor blade diameter of 1.5 meters. This size was crucial. Larger aircraft would have been overwhelmed by the Martian atmosphere, which is roughly 100 times thinner than Earth's. The rotor blades were constructed from lightweight carbon fiber composite materials, meticulously engineered to withstand the harsh conditions. They were incredibly sensitive, designed to capture even the smallest gusts of wind. Each blade was covered in a durable, heat-resistant coating to protect it from the extreme temperature swings of the Martian surface, which could range from -80 degrees Celsius to 20 degrees Celsius. The helicopter was equipped with a small, efficient electric motor and batteries, providing the power needed to turn the rotor blades. The biggest challenge wasn't the materials or the motor, though. It was the control system. Ingenuity relied on a sophisticated system of sensors, including inertial measurement units, IMUs, tiny devices that measure acceleration and rotation, and barometers to gauge the atmospheric pressure. This data was fed into a flight control computer, which constantly adjusted the rotor speed to maintain stability. The computer used sophisticated algorithms, essentially complex sets of instructions, to counteract any tendency for the helicopter to wobble or spin. The control system essentially acted as the pilot, constantly making tiny adjustments to keep Ingenuity flying straight and true. The first flight was a moment of breathtaking tension. On December 2, 2021, after a week of preparation and several unmanned test flights, Ingenuity was remotely activated. The rotor blades spun to life, and the helicopter hovered briefly, kicking up a small cloud of dust. It was the first powered, controlled flight on another planet. The data streamed back to Earth, confirming that the flight had been successful. It lasted just 39 seconds, covering a distance of 20 meters, but it was a monumental achievement. It demonstrated that a small, lightweight aircraft could operate effectively in the Martian atmosphere. Subsequent flights steadily increased in duration and distance. Ingenuity's performance was remarkable. It consistently exceeded expectations, becoming increasingly adept at navigating the complex terrain around the Perseverance landing site. The data it collected was invaluable. It identified potential hazards, such as rocks and slopes, providing Perseverance with a detailed, three-dimensional map of the area. It also captured stunning images of the Martian landscape, revealing hidden features and providing scientists with a new perspective on the planet's geology. The flight data also provided crucial insights into the Martian atmosphere. Ingenuity's sensors measured wind speeds and turbulence, which helped scientists better understand the complex dynamics of the Martian atmosphere. This knowledge is essential for future Mars missions and for developing strategies for exploring the planet. It wasn't just about the flight itself, it was about the information Ingenuity was gathering. As the mission progressed, Ingenuity's flight profile evolved. It began to use its flight capabilities to assist Perseverance in reaching its primary scientific goals. For example, it was used to survey areas of interest for Perseverance's sample collector, pinpointing the best locations to collect rock samples for eventual return to Earth. The helicopter acted as an airborne scout, relaying critical information to the rover. The ability to operate autonomously, making decisions based on sensor data and pre-programmed instructions, was a key advancement. The team rigorously monitored Ingenuity's performance, making small adjustments to the flight plan to optimize its efficiency and safety. They were constantly refining the control algorithms and testing new flight techniques. They even began experimenting with different flight modes, such as hovering and forward flight. Ingenuity became more than just a scout. It was evolving into a sophisticated aerial platform. The entire operation was a testament to human ingenuity and the power of collaboration. The mission wasn't without its challenges, of course. There were times when Ingenuity experienced unexpected gusts of wind or encountered obstacles. But the team responded quickly and effectively, implementing corrective measures and continuing to push the boundaries of what was possible. The helicopter demonstrated remarkable resilience and adaptability. As the planned operational life of Ingenuity drew to a close, the team made the difficult decision to end its mission. The conditions on Mars were becoming increasingly challenging, and the risk of damage to the helicopter was growing. But even in its final flights, Ingenuity continued to provide valuable data and inspire awe. It left a lasting legacy, proving that powered flight on Mars was not just a dream but a tangible reality. The story of Ingenuity is a captivating example of how a small, seemingly simple project can have a profound impact on our understanding of another world. It's a story of innovation, perseverance, and the relentless pursuit of knowledge. It's a reminder that even the most ambitious goals can be achieved through careful planning, dedicated teamwork, and a little bit of courage. As Ingenuity's final flight concluded, it carried with it a message of hope and a promise of future exploration, a promise that humanity will continue to reach for the stars. The reddish hue of Mars, a color so familiar now, isn't just a trick of the light or the dust settling. It's a significant part of the story of the planet's surface, a story now being written in detail by instruments and robots exploring the Martian soil. While the presence of ancient water and the possibility of past life were exciting discoveries, the true puzzle presented by Mars' surface has been the composition of the soil itself, specifically the surprising abundance of chemicals that pose a considerable challenge to any potential life, or even to human colonization. The initial observations from the Viking landers in the 1970s hinted at something unusual, But it wasn't until more sophisticated analysis, particularly by the Curiosity rover, and more recently, the Perseverance mission, that the full extent of the problem perchlorates began to be understood. These perchlorates, compounds containing chlorine and oxygen, are incredibly common on Mars. They're found in significant quantities in the Martian regolith, the loose, weathered surface material covering the planet. Initially, scientists suspected small amounts, but the data coming back from Curiosity's CAM instrument, and especially the sample analysis at Mars, SAM, revealed concentrations far exceeding what was expected. The SAM instrument, a marvel of miniaturized chemistry, could precisely measure the abundance of gases released when the soil was heated, effectively burning it to reveal its chemical makeup. The repeated analysis of Martian soil samples consistently showed levels of perchlorates, primarily magnesium perchlorate and calcium perchlorate, that were shockingly high, sometimes reaching several percent by weight. This wasn't a trace element. It was a major component of the surface material. The significance of these perchlorates isn't simply their presence, it's their effect on water. Water is, of course, the lifeblood of our planet, and it's almost certainly been a vital ingredient in the history of Mars. However, when water interacts with perchlorates, it undergoes a chemical reaction that produces corrosive and damaging compounds. The water molecules break down, and the perchlorates are transformed into highly reactive acids, hydrochloric acid and sulfuric acid, primarily, along with chlorine dioxide. This isn't a dramatic, immediate flash, but a slow, insidious process. The acids attack and degrade organic materials. They break down amino acids, the building blocks of proteins and nucleic acids, the molecules that carry genetic information like DNA. In essence, they dismantle the very foundations of life as we know it. The implications for habitability are profound. If microbial life, perhaps simple organisms similar to those found in extreme environments on Earth, had ever existed on Mars, these perchlorates would have rendered their existence extraordinarily difficult, if not impossible. The acids would have continuously attacked and destroyed any delicate organic structures. It's like trying to build a castle on sand. The corrosive chemicals relentlessly undermine the foundations. Even if some resistant, highly adapted microbes could have survived, the conditions would have been overwhelmingly hostile. Perseverance's mission is, in part, dedicated to understanding this process. The rover isn't just collecting samples for potential return to Earth. It's actively studying the degradation of organic matter in the presence of perchlorates. It's equipped with instruments designed to measure the rate at which different organic compounds break down under various conditions, different temperatures, different amounts of water, simulated through the addition of meltwater, and varying concentrations of perchlorates. The rover is essentially conducting a long-term experiment, observing how the Martian soil itself alters over time. This data is crucial for refining models of Mars, past habitability, and for assessing the challenges associated with future human missions. Furthermore, scientists are investigating ways to mitigate the effects of perchlorates. One promising avenue is the use of heat to break down the perchlorates, before any organic material can be studied. The SAM instrument, combined with advanced heating techniques, is demonstrating the potential to remove perchlorates from samples, allowing for a more accurate analysis of the original organic content. This is a critical step towards understanding if any truly preserved evidence of past life exists within the Martian soil. Another strategy involves exploring the possibility of using microbes themselves, specifically terrestrial microbes adapted to harsh conditions, to neutralize the perchlorates. While this is a more speculative approach, it highlights the ingenuity being applied to tackle this complex problem. The return of the Perseverance rover's samples is perhaps the most exciting development in this ongoing story. These samples, carefully sealed and preserved, represent a time capsule of the Martian soil, a record of the planet's chemical history. Once returned to Earth, scientists will be able to conduct incredibly detailed analyses using instruments far more sophisticated than anything that can be deployed on Mars. They'll be able to precisely quantify the perchlorate concentrations, study the breakdown pathways of organic molecules, and potentially even identify any microscopic traces of past life, shielded perhaps by protective minerals within the rock. Ultimately, understanding the perchlorate problem isn't just about Mars' past. It's about informing our plans for the future. If humans ever intend to establish a permanent presence on Mars, a thorough understanding of these corrosive chemicals is absolutely essential. It will dictate the design of habitats, the selection of landing sites, and the strategies for resource utilization. The Martian soil, once seen as simply a reddish backdrop, is now revealed as a complex and challenging environment, a silent witness to the planet's history, and a critical factor in determining its future. The ongoing exploration and analysis of the Martian soil are a testament to the enduring human curiosity and our relentless pursuit of knowledge, even and perhaps especially in the face of daunting scientific puzzles. The surface of Mars, as we've seen, is a challenging place. It's sculpted by fierce winds, bombarded by radiation, and often covered in a rusty dust that obscures what lies beneath. While the Perseverance rover's cameras and spectrometers gave us incredible images and chemical analyses of the immediate surroundings, they couldn't, on their own, reveal the true shape and extent of what's hidden just below the ground. That's where radar technology came in, a powerful tool that uses radio waves to see through the Martian landscape. Radar, at its core, is based on a simple principle. When a radio wave is sent out, it bounces off objects. The time it takes for the wave to return, combined with the known speed of radio waves, allows scientists to calculate the distance to that object. Now, Mars is mostly made of rock and ice, and these materials interact with radio waves in a way that's quite different from how they behave here on Earth. In fact, the Martian subsurface is surprisingly complex. Beneath the relatively smooth, rocky surface, there are layers of sediment, buried glaciers, and potentially even ancient riverbeds, all waiting to be discovered. The Mars Reconnaissance Orbiter, MRO, launched in 2006, was equipped with a radar instrument called SHARAD, the SHARAD Synthetic Aperture Radar. SHARAD isn't like the radar you might find in a car. It's a sophisticated instrument that transmits and receives a wide range of radio waves. The key is its ability to produce extremely detailed images, much like a high-resolution photograph. But instead of light, it uses radio waves. It achieves this by moving the antenna rapidly and measuring the changes in the returning signals. This creates a synthetic aperture, effectively making the radar antenna much larger than it actually is. The data collected by SHARAD has revealed some truly remarkable things about Mars. One of the most significant discoveries has been the evidence of vast, buried deposits of water ice. These aren't just small patches. We're talking about massive, kilometer-wide ice layers hidden beneath the surface. These deposits are particularly concentrated in the mid-latitudes of Mars, where the ground is cooler and the conditions are more favorable for ice preservation. SHARAD's ability to penetrate several meters into the ground allows scientists to identify these subsurface ice reserves, which are of great interest for future human missions. A readily available resource for water, oxygen, and potentially even rocket fuel. Beyond ice, SHARAD has also detected evidence of layered sedimentary deposits. These are formations created by the accumulation of sediment over long periods of time, similar to how riverbeds are formed on Earth. However, on Mars, these sediments haven't been shaped by flowing water. They were formed by the accumulation of dust and sand carried by ancient winds. The radar data suggests that Mars may have once had extensive river systems, far larger than those we see today. These ancient riverbeds, buried beneath the surface, are like frozen time capsules, preserving a record of Mars's past climate and geology. Another fascinating finding has been the detection of what scientists are calling chaos terrain. These are regions of disrupted, blocky terrain, often characterized by sharp, angular rocks scattered across a relatively flat surface. SHARAD has shown that these features often extend quite deeply beneath the surface, suggesting that they were formed by the movement of buried ice, essentially giant ice blocks sliding across the Martian crust. The way SHARAD works is particularly effective in identifying features that are difficult to see with optical instruments. Dust storms, for example, can completely obscure the surface, making it impossible to take a clear photograph. However, SHARAD can still penetrate the dust and produce detailed images of the subsurface. This is incredibly valuable for monitoring changes in the Martian landscape and understanding the impact of dust on the planet's climate. Furthermore, SHARAD's data has revealed the presence of subsurface slopes and dips that are not visible on the surface. These features are created by the gradual erosion of the Martian soil by wind and ice. By mapping these subsurface slopes, scientists can gain a better understanding of the planet's geological history and predict how the landscape will evolve over time. The data from SHARAD is constantly being analyzed and refined. Scientists are using sophisticated computer models to interpret the radar signals and create three-dimensional maps of the Martian subsurface. These maps are being used to guide future exploration missions, helping scientists identify the most promising locations for landing and searching for evidence of past life. It's important to remember that SHARAD is just one piece of the puzzle. The data it provides is often combined with information from other instruments, such as the Perseverance rover's cameras and spectrometers, to create a more complete picture of Mars's geology. The synergy between different instruments and data sets is crucial for unlocking the secrets of this fascinating planet. Looking ahead, future missions are planned to further enhance our understanding of the Martian subsurface. New radar instruments, with even greater resolution and sensitivity, will be deployed to probe deeper into the ground and create even more detailed maps. These advancements will undoubtedly lead to new discoveries and transform our knowledge of Mars, potentially revealing even more evidence of its watery past and its future role in the exploration of our solar system. The continued use of radar technology is a testament to our ingenuity and our persistent desire to understand the worlds beyond our own. The red planet, Mars, isn't just a rusty color. It's a world constantly sculpted by the wind, and a significant part of that sculpting is driven by something truly spectacular: dust storms. These aren't the fluffy, gentle clouds we see on Earth. Martian dust storms are colossal events, capable of dramatically altering the planet's atmosphere and impacting every rover, lander, and future human mission. Scientists have been diligently studying these storms, trying to understand their unpredictable nature, how strong they get, and exactly what they're doing to the air around them. Initially, it seemed Mars would be perpetually shrouded in a thin haze, but observations quickly revealed a surprising frequency of dust storms. While small, localized storms happen regularly, often triggered by the sun heating specific regions, what truly captured the attention of planetary scientists were the global, or planetary, dust storms. These events, sometimes called Barkhan storms, can envelop the entire planet, dramatically darkening the surface and causing significant changes in temperature. The frequency of these large storms isn't constant. It waxes and wanes over Martian years, which are about twice as long as Earth years. Researchers believe this cyclical behavior is tied to the planet's axial tilt, the angle at which Mars spins on its axis, and its orbital position relative to the Sun. As Mars moves through its orbit, the amount of sunlight it receives changes, influencing the temperature differences that initiate the storms. The intensity of these storms is astonishing. Measurements taken by rovers like Curiosity and Perseverance, and even orbital satellites, have revealed that dust particles can reach incredibly high altitudes, sometimes extending hundreds of kilometers above the surface. These particles aren't just swirling around, they're creating a truly dynamic and turbulent atmosphere. The storm's strength is judged based on how much sunlight they block from the surface, and how much they raise the atmospheric opacity, making the sky a thick, ochre-colored haze. Scientists use spectrometers, instruments that analyze the light reflected from the dust, to determine the size and concentration of the particles, providing a crucial measure of the storm's severity. The largest dust storms, often lasting weeks or even months, can drastically reduce the amount of sunlight reaching the surface, chilling the planet and temporarily disrupting solar-powered operations. The atmospheric effects of these storms are multifaceted and profoundly impactful. One of the most significant is the creation of a haze layer. As dust is lifted into the atmosphere, it scatters sunlight, creating this widespread haze. This haze isn't uniform, it's affected by the storms themselves. During a storm, the haze becomes significantly thicker, blocking even more sunlight. Furthermore, the dust interacts with the Martian atmosphere, influencing its chemical composition. The heating caused by the dust absorbs certain wavelengths of sunlight, affecting the temperature profile of the atmosphere. The storms also impact the movement of the atmosphere, creating powerful winds that can travel thousands of kilometers across the planet. Scientists have developed sophisticated models to simulate dust storm behavior, but predicting these events remains incredibly challenging. The complex interplay of solar heating, atmospheric circulation, and surface topography creates a chaotic system. Data collected by the Mars Reconnaissance Orbiter's cameras and spectrometers has been invaluable in refining these models. The orbiter's high-rise instrument, in particular, has provided stunning close-up images of dust storm dynamics, revealing intricate patterns of swirling dust and the way the storms interact with the landscape. These images are not just beautiful, they offer critical clues about the processes driving the storms. Beyond simply observing the storms, researchers are actively investigating the source of the dust. It's believed that the majority of the dust originates from the vast, ancient plains, the Planum Austral at the South Pole. These regions are covered in dark, salty material, and when the sun shines on them, the ground heats up, causing the dust to become airborne. The wind then carries this dust across the planet. Studying the composition of the dust, its mineral content and particle size, helps scientists understand the geological history of Mars and the processes that shape its surface. The impact of dust storms isn't solely detrimental. While they pose a significant hazard to robotic missions, they also play a crucial role in shaping the Martian environment. The dust acts as a natural regulator, distributing heat and influencing atmospheric circulation. It also serves as a vital source of material for the planet's evolving landscape. The ongoing study of Martian dust storms is therefore central to our understanding of Mars's past, present, and potential future, and is fundamentally important for ensuring the safety and success of any future human exploration efforts. Continued observation and research are revealing more about this turbulent, red world. The Curiosity rover, after its initial explorations of the lower slopes of Mount Sharp, began a methodical ascent, a journey into the heart of Gale Crater. This wasn't a simple climb. It was an investigation of a layered history, a geologic time capsule revealing Mars' past. Mount Sharp, officially named Aeolis Mons, is a massive, central peak, roughly 5.5 miles tall, and its formation is the key to understanding why Curiosity is there. The crater itself formed billions of years ago, likely from an asteroid impact. But what happened afterward, how the landscape built up, was the really exciting puzzle. The scientists hypothesized that Gale Crater had once been a large lake, and Mount Sharp was formed by sediment accumulating over eons, much like river deltas building up on Earth. Curiosity's mission was to study these different layers, the sedimentary rocks, to determine when and how the lake existed and what conditions were like during that time. These layers weren't uniform. They were incredibly diverse, ranging from fine-grained clays at the bottom to coarser sands and conglomerates higher up. Each layer represented a different period of deposition, influenced by fluctuating lake levels, changing weather patterns, and possibly even the activity of ancient rivers. The rover meticulously analyzed the composition of each layer, using its suite of instruments to determine the minerals present, their textures, and their relationships to one another. It employed the Mastcam to capture high-resolution images of the rock formations, providing a visual record of the changes in the landscape. The ChemCam laser instrument proved invaluable, allowing Curiosity to zap rocks with a laser beam and analyze the chemical elements within, again, offering a snapshot of the material's makeup. The lower layers of Mount Sharp were dominated by fine-grained sediments, clays, shales, and mudstones. These clays were particularly intriguing because they contained hydrated minerals, meaning they held water molecules within their structure. This was significant because the presence of water is a fundamental requirement for life as we know it. Curiosity detected evidence of phyllosilicates, a group of clay minerals, which indicated prolonged exposure to water. These lower layers potentially represent a period when Gale Crater was filled with a relatively calm, deep lake, with water levels stable enough to allow for extensive clay formation. The rover's sample analysis at Mars, SAM, instrument was used to heat samples, releasing gases that provided insights into the original composition of the rocks, including the detection of organic molecules, the building blocks of life, although their origin remained a subject of intense investigation. As Curiosity climbed higher, the layers became coarser and more diverse. It encountered rocks containing sand-sized grains, gravel, and even larger boulders, evidence of rivers and streams flowing into the lake. These upper layers represented a more dynamic period, with fluctuating water levels and increased erosion. The rover found conglomerates, which are sedimentary rocks composed of rounded pebbles and larger rocks cemented together, revealing that rivers had actively transported and deposited material within the crater. The data collected from these layers helped scientists build a more detailed timeline of Gale Crater's history, recognizing that the environment changed dramatically over millions of years. A crucial aspect of the investigation was analyzing the layering's vertical extent. Curiosity wasn't just studying individual rocks, it was studying how the rocks stacked upon each other. By meticulously documenting the variations in sediment type and the presence of different minerals, scientists were able to reconstruct the sequence of events that formed Mount Sharp. For example, they found evidence of repeated flooding events, where the lake levels rose dramatically, depositing thick layers of sediment. This pattern mirrored similar geological processes on Earth, where rising sea levels can create distinct sedimentary layers. The rover's rock abrasion tool, also known as the drill, was used to obtain powdered samples from some of the rocks, allowing for more detailed chemical analysis and minimizing the impact of contamination. The analysis of the layering also revealed information about the climate of Mars during its early history. The types of minerals present in the different layers correlated with different temperature and humidity conditions. For instance, the presence of sulfates in the higher layers indicated drier, warmer conditions, while the clays in the lower layers suggested cooler, wetter conditions. Understanding these climate changes is vital because it helps scientists assess the potential habitability of Mars at different points in its past. Furthermore, Curiosity's data contributed to a growing understanding of the processes that shaped the Martian surface. It wasn't simply a collection of sedimentary rocks. It was a record of the planet's geological evolution, the forces that acted upon it over billions of years. The data continues to be analyzed and debated, refining our understanding of this ancient environment, and perhaps one day, offering further clues about the possibility of past life on the red planet. The mission continues to reveal new details, solidifying Mount Sharp as one of the most scientifically valuable locations ever explored. The Perseverance rover, diligently traversing the slopes of Jezero Crater's Mount Sharp, wasn't simply collecting rocks to study their composition. It was engaged in a far more profound quest, a detailed investigation into the history of volcanic activity on Mars. While the crater itself holds compelling evidence of an ancient lake and river system, the mountain at its center, formed from layered sedimentary rock, presents a vital puzzle. Did volcanic forces play a significant role in shaping this landscape, or was it solely sculpted by water and wind? Scientists theorize that Mars, billions of years ago, possessed a far more active interior than it does today, and the quest to understand the extent of that activity is a central thread in unraveling the planet's past. Perseverance's primary tool in this investigation isn't a single instrument, but rather a suite of capabilities, all focused on detecting and analyzing subtle clues. The rover's Mastcam-Z, a sophisticated stereo imaging system, has been particularly valuable. These cameras don't just take pictures. They meticulously map the 3D structure of the rocks, identifying features like fractured surfaces, slumped blocks, and altered rock textures. These anomalies are often direct results of volcanic processes. For example, the rover has observed extensive, jigsaw-like fracturing in some of the layered rocks, a pattern frequently associated with the cooling and contraction of magma. These breaks aren't random. They suggest that the rock was heated from within, likely by intrusions of molten material. Furthermore, Perseverance utilizes its SuperCam instrument, a powerful laser-based spectrometer, to analyze the elemental composition of rocks at a distance. SuperCam can detect the presence of minerals that are typically formed in volcanic environments. Specifically, it's searching for evidence of minerals like pyroxene and olivine, which are common constituents of basalt, a volcanic rock that makes up a large portion of the Martian crust. The instrument's ability to identify these minerals, even from afar, allows it to assess the overall volcanic influence on a region. It's like a geological fingerprint, revealing the types of magma that were present and the conditions under which they cooled. Beyond visual and chemical analysis, Perseverance is also collecting samples of rock and sediment, carefully documenting their location and characteristics. These samples are critical because they're intended to be returned to Earth for even more detailed study. The samples collected from areas with pronounced volcanic features, such as a region named Bright Angel, are of particular interest. These locations show clear signs of hydrothermal alteration, where hot, chemically rich water circulated through the rocks, often associated with volcanic activity. The presence of hydrated minerals like clays and sulfates in these areas strongly suggests that volcanic heat drove the interaction between magma and groundwater. The rover's RIMFAX radar instrument provides another crucial perspective. While RIMFAX was initially developed to map subsurface geological structures, it has also proven invaluable in detecting buried volcanic features. By sending out radio waves and analyzing the echoes, RIMFAX can penetrate beneath the surface, identifying variations in rock density and the presence of subsurface magma bodies. Discoveries made using RIMFAX have revealed what appear to be ancient lava tubes, collapsed volcanic structures, and areas of unusually high heat flow, hinting at a more complex and dynamic volcanic history than previously suspected. Data relayed from the Ingenuity helicopter, though primarily designed for aerial reconnaissance, has also contributed to this investigation. The helicopter's high-resolution images provide a unique vantage point, allowing scientists to observe the broader context of volcanic features and assess their relationship to the surrounding terrain. Furthermore, Ingenuity's ability to identify areas of thermal anomaly, regions that are significantly warmer than their surroundings, can be correlated with RIMFAX data to pinpoint potential subsurface volcanic activity. Scientists believe that Mars experienced several periods of intense volcanic activity, possibly linked to the planet's early formation and subsequent differentiation. The process of separating heavier elements like iron and nickel from lighter ones. Evidence suggests that massive shield volcanoes, vast, gently sloping structures built up by repeated lava flows, once dominated the Martian landscape. While most of these large volcanoes have eroded away over billions of years, smaller, more localized volcanic features persist, offering invaluable clues about the planet's past. The analysis of Martian meteorites, which have landed on Earth, has also played a significant role. These meteorites, originating from Mars, provide a tangible record of the planet's interior and a broader range of volcanic materials than are typically accessible on the surface. Their study allows scientists to examine the chemical composition and textures of Martian volcanic rocks in a controlled laboratory environment, furthering our understanding of the processes that shape the planet. Ultimately, the search for evidence of past volcanic activity on Mars is not simply about identifying extinct volcanoes. It's about reconstructing the planet's entire geological history, understanding how Mars evolved, how it interacted with water, and whether conditions ever existed that might have supported microbial life. The layered rocks of Mount Sharp, the subtle fractures in the surrounding terrain, and the meticulously collected samples all hold the potential to rewrite our understanding of the red planet. The journey to Mars, a dream held for centuries, is rapidly shifting from science fiction to a tangible possibility. But before humans can set foot on the red planet and truly begin to explore its mysteries, a significant hurdle must be overcome: the pervasive and dangerous radiation environment. Mars lacks a global magnetic field, like Earth's, which deflects harmful charged particles from the Sun and, to a lesser extent, from interstellar space. This absence leaves astronauts exposed to a constant bombardment of radiation, a risk that demands meticulous understanding and sophisticated solutions. The primary source of radiation on Mars isn't a sudden, explosive solar flare, although those events can dramatically increase the risk. Instead, it's a relentless stream of particles, mostly protons and electrons, originating from the constant solar wind. The solar wind is a stream of charged particles ejected by the Sun, and even when the Sun appears calm and quiet, this wind is still flowing outwards, impacting the Martian atmosphere and, consequently, any spacecraft or human presence on the planet. These particles are energetic and possess enough momentum to penetrate shielding materials, depositing their energy within the bodies of astronauts. Beyond the solar wind, cosmic rays pose a considerable threat. These are high-energy particles, originating from supernovae, the explosive deaths of massive stars that have traveled across vast distances of space. Unlike the solar wind, which follows the Sun's magnetic field, cosmic rays are not tied to any particular direction. They arrive randomly, and some are incredibly powerful, potentially causing severe radiation damage. The intensity of cosmic ray flux varies depending on the level of solar activity, with periods of increased solar activity leading to a higher dose. Measuring this radiation exposure isn't straightforward. Instruments onboard spacecraft provide data, but interpreting that data and predicting the level of radiation at a specific location on Mars requires complex models. These models account for solar wind conditions, cosmic ray intensity, and the planetary atmosphere's ability to scatter and absorb radiation. Current estimates suggest that an astronaut on a 6-month surface mission could receive a radiation dose approximately 20 to 30 times higher than the annual radiation limit considered safe for humans on Earth. This isn't a single, overwhelming burst, but the cumulative effect over an extended mission is profoundly concerning. The consequences of this radiation exposure are potentially devastating. Acute radiation sickness, similar to what some people experience after a nuclear accident, is a possibility. Symptoms can range from nausea and vomiting to skin burns, and in severe cases, damage to the central nervous system. However, the more insidious and long-term effects are arguably more worrisome. Prolonged exposure dramatically increases the risk of developing cancer, particularly leukemia. It can also damage DNA, potentially leading to genetic mutations that could affect future generations. Furthermore, radiation exposure can impair cognitive function and potentially cause neurological disorders. Fortunately, scientists and engineers are developing a range of mitigation strategies. One approach focuses on shielding. Traditional shielding materials like aluminum offer limited protection against radiation. Therefore, researchers are investigating more effective materials, including water. Surprisingly, water is an excellent radiation shield due to its high hydrogen content, which readily interacts with incoming radiation particles. Other promising materials include polyethylene, regolith Martian soil, and even advanced composites. The design of habitats is crucial. Pressurized rovers and habitats can provide a significant degree of shielding, but their effectiveness depends on the thickness and composition of the walls. Furthermore, careful placement of habitats in areas with naturally occurring geological features, such as lava tubes or subsurface caves, could offer substantial protection from radiation. These underground environments have been shaped by millennia of geological processes and provide a natural shield against both solar and cosmic radiation. Another critical strategy involves minimizing the time astronauts spend exposed to radiation. This can be achieved through careful mission planning, utilizing trajectory corrections that reduce exposure, and employing advanced spacecraft designs that allow for rapid transit. Robotic precursors could be sent to Mars to scout locations, assess radiation levels, and potentially construct initial habitats before human arrival, further reducing the immediate radiation risk. Furthermore, real-time monitoring and prediction systems are being developed. These systems would continuously track radiation levels and provide astronauts with timely alerts, allowing them to take protective measures, such as sheltering in shielded areas. Advanced algorithms could analyze data from multiple sources, including solar wind measurements, spacecraft sensors, and planetary models, to predict radiation events with increasing accuracy. Pharmaceutical interventions are also being explored. Researchers are investigating drugs that could potentially mitigate the harmful effects of radiation, such as antioxidants that could neutralize free radicals produced by radiation damage. However, the development of effective radiation countermeasures is a complex and long-term endeavor. Finally, the use of artificial magnetospheres represents a longer-term and considerably more ambitious solution. Concepts are being investigated to create a localized magnetic field around a habitat or spacecraft, effectively deflecting harmful radiation particles. This could involve deploying a system of superconducting coils or utilizing plasma propulsion to generate a magnetic field. Successfully tackling the radiation challenge is not just a matter of safety. It's fundamentally about unlocking the potential for a sustainable and productive human presence on Mars. The journey to the red planet demands not only technological innovation, but also a deep understanding of the inherent risks and a commitment to developing the strategies necessary to overcome them. The future of Martian exploration hinges, in large part, on our ability to shield our pioneers from the pervasive, yet ultimately manageable, dangers of the radiation environment. The red dust of Mars hangs in the air, a fine, pervasive powder that coats everything it touches. It's beautiful, really, in its muted tones, and yet it's also the key to understanding one of the biggest puzzles about this fascinating planet. That puzzle centers around the atmosphere, or rather, the distinct lack of one. Mars possesses an atmosphere, but it's extraordinarily thin, just a tiny fraction of Earth's. Scientists estimate it's roughly 100 times less dense, meaning it exerts a remarkably small amount of pressure at the surface. This drastically different atmospheric environment presents immense challenges for any possibility of habitability, and crucially, for the design of vehicles intended to operate on the planet. The composition of the Martian atmosphere is also strikingly different. Primarily, it's made up of carbon dioxide, about 96%. There's a small percentage of argon and nitrogen, and minuscule amounts of other gases like oxygen and methane. The incredibly low concentration of oxygen is the most significant hurdle. Humans, and indeed most life as we know it, require a substantial amount of oxygen to breathe. Even with sophisticated life support systems, sustaining a human presence on Mars would demand constant, heavy-duty oxygen production, a process that consumes enormous amounts of energy. Furthermore, the low oxygen levels contribute to the overall problem of atmospheric retention. The thin atmosphere is incredibly easy to escape. The low pressure has cascading effects on various physical processes. Liquids don't boil or freeze at the same temperatures as on Earth. Water, for example, boils at just 15 degrees Celsius. That's room temperature. This means that any liquid water on the surface would rapidly evaporate into the atmosphere. This has profound implications for the search for subsurface water, a crucial element for potential life, as the surface water would be fleeting. The rapid evaporation also creates a constant cycle of sublimation. The direct transition of ice from a solid to a gas, further reducing the amount of accessible water. Beyond water, the atmospheric thinness dramatically influences temperature regulation. Without a substantial atmosphere to trap heat, Mars experiences extreme temperature swings. During the day, the sun's radiation passes through the thin atmosphere with minimal absorption, leading to very high temperatures, particularly near the equator. Conversely, at night, with no atmosphere to retain the heat, temperatures plummet, often reaching incredibly low levels, far below what would be survivable without significant insulation. These dramatic temperature shifts pose a significant threat to both equipment and any potential life forms. This atmospheric characteristic fundamentally shapes the design of spacecraft and rovers intended for Mars missions. Traditional rocket propulsion relies on burning propellants, and the thin atmosphere significantly reduces the efficiency of this process. Rockets must expend a considerable amount of energy simply to overcome the atmospheric drag, limiting the amount of payload they can carry, including scientific instruments and resources. Engineers have therefore been exploring alternative propulsion systems, such as solar sails and ion drives, which don't require burning propellants and can operate effectively in the thin atmosphere. Vehicle design also needs to account for the constant bombardment of micrometeoroids. Because the atmosphere is so thin, there are very few particles to impede them. This means that spacecraft and rovers are constantly exposed to a stream of tiny, high-speed particles, posing a risk of damage to sensitive instruments and structural components. Shielding, incorporating materials designed to deflect or absorb these impacts, is therefore a critical element of vehicle design. The low atmospheric density impacts communications too. Radio waves, the primary means of communication between Earth and Mars, travel through the atmosphere. The thin atmosphere offers significantly less resistance to these waves compared to Earth's denser atmosphere, leading to increased signal strength and range. However, this also means that signals can be more easily scattered, potentially impacting the reliability of communications, particularly over longer distances. Furthermore, dust, that ubiquitous red dust, plays an important role. The extremely low atmospheric pressure makes dust particles incredibly light and easily lofted into the air by even the smallest breeze. This creates a perpetual haze that reduces visibility, complicates operations for rovers and astronauts, and can damage equipment. Dust mitigation strategies, including specialized seals, cleaning systems, and protective coatings, are vital for any surface operations. The challenges presented by Mars' thin atmosphere are not merely technical hurdles. They represent fundamental obstacles to the possibility of creating a sustainable human presence on the planet. It demands innovative engineering, meticulous planning, and a deep understanding of the complex interactions between the planet's environment and any technologies we bring with us. As we continue to explore, learning to adapt to and overcome these atmospheric constraints will be essential to unlocking the secrets of Mars and determining whether it can truly become a second home for humanity. The red dust whispers its challenges, and our response will ultimately define our success. The rover Perseverance, diligently traversing the Jezero crater, had revealed so much about Mars's ancient past. The sediments shaped by a vanished lake, the signs of fluvial processes suggesting a warmer, wetter environment. But the science team, tirelessly analyzing data from the rover and orbiting spacecraft, began to suspect a story wasn't quite finished. They realized that the evidence for past water wasn't solely confined to the crater's bottom. It seemed Mars was holding onto its water in a very different and surprisingly accessible location: the equatorial regions. Early data from the Mars Reconnaissance Orbiter's Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, had hinted at hydrated minerals, but the signals were weak and often obscured by dust. The challenge was to refine the techniques to identify and map these minerals with greater precision. Advances in radar technology, particularly the SHARAD instrument aboard the orbiter, provided a significant breakthrough. SHARAD sends out radio waves and measures how long they take to bounce back from different materials. This allows scientists to create a detailed 3D map of the subsurface, essentially seeing through the Martian surface. The key discovery came unexpectedly. The team noticed persistent, bright radar reflections from areas near the Martian equator, Initially, they considered these to be echoes from large, exposed rock formations. However, the characteristics of these reflections, their strength, their depth, and their spatial distribution, didn't fit the profiles of typical bedrock. The data suggested something much more interesting: a significant volume of material with a high water content buried just beneath the surface. These weren't just surface features. The radar signals indicated deposits extending down to several meters, and in some cases, even 10 meters deep. The most compelling evidence came from several locations, notably within the Medusi Fossi Formation, a vast, ancient deposit located roughly 350 kilometers north of Gale Crater. This formation, already known to be a target for future exploration, was proving to be an incredibly rich source of potential water ice. The ice wasn't uniformly distributed. It existed in layers, interspersed with darker, drier sediments. This layering strongly suggested that the ice had been repeatedly deposited and buried over billions of years, a consequence of Mars's changing climate. The precise composition of the ice was a subject of intense investigation. Spectroscopic data, gathered by Perseverance and other instruments, confirmed the presence of water-bearing minerals like phyllosilicates, clay minerals that form when silicate rocks are altered by water. The abundance of these minerals pointed to prolonged contact with liquid water in the past. Furthermore, the detection of perchlorates, salts that can stabilize water ice and lower its melting point, added another layer of complexity. These salts, while challenging for human explorers due to their reactivity, also contribute to the preservation of the ice. What was particularly remarkable was the relatively shallow depth of these deposits. Unlike the polar ice caps, which are buried under kilometers of ice and dust, the equatorial ice was found just a few meters below the surface in many areas. This accessibility is hugely significant. It means that, theoretically, the ice could be accessed relatively easily for future human missions or for robotic resource utilization. The ice could be melted to provide water for drinking, for growing plants, or even for producing rocket fuel, a crucial step in establishing a sustainable presence on Mars. Scientists developed sophisticated models to estimate the total volume of ice present in the equatorial region. The estimates were staggering, suggesting that Mars may hold significantly more water ice than previously thought. This newfound abundance of water ice dramatically alters our understanding of Mars's potential for habitability and resource availability. It wasn't simply a question of whether Mars had water. It was now clear that a substantial amount was readily accessible, albeit in a challenging environment. The discovery also prompted a reassessment of Mars's climate history. The presence of equatorial ice suggests that Mars wasn't always a frigid, barren world. There were periods in the past when the equatorial regions were warmer and wetter, conditions that might have been suitable for microbial life. This discovery reinforces the argument that Mars was once a far more dynamic and potentially habitable planet. The ongoing exploration continues to refine our understanding. Rovers are being deployed to conduct detailed investigations of these deposits, analyzing the ice's purity and searching for any signs of organic molecules, the building blocks of life. The data collected will allow scientists to create a more detailed picture of Mars's hydrological history and assess the true potential for utilizing this abundant resource. The search for evidence of past life on Mars is now inextricably linked to the accessibility of this newly discovered water ice. It's a compelling testament to the persistent curiosity driving the exploration of the Red Planet. The rovers, Perseverance and Curiosity, weren't just collecting rocks and dust. They were essentially tiny, mobile laboratories, constantly sniffing the Martian air. One of the most perplexing and exciting aspects of their work has been the detection of significant levels of atmospheric gases, particularly methane and carbon dioxide, and the persistent question of where these gases originate. The early data from the Viking landers in the 1970s hinted at a carbon dioxide-rich atmosphere, but the measurements coming from the modern rovers revealed a far more complex picture. Carbon dioxide dominates the Martian atmosphere, making up roughly 96% of its composition. This is a consequence of the planet's lack of a significant magnetic field, which allows the solar wind, a constant stream of charged particles from the sun, to strip away lighter gases like oxygen and hydrogen over billions of years. The residual atmosphere is incredibly cold, leading to almost all of the carbon dioxide existing as dry ice in the polar caps and as frost on the surface, especially in shaded areas. However, the levels of methane detected were far more intriguing. Initial detections in 2013 by Curiosity's sample analysis at Mars SAM instrument were fleeting, short bursts of methane fluctuating in concentration. These readings sparked intense debate. Methane is a relatively unstable gas in the Martian environment, quickly broken down by ultraviolet radiation from the sun. Therefore, a sustained, detectable level suggested an ongoing source. The challenge was identifying that source. The SAM instrument, utilizing pyrolysis, heating the gas to break it down into its constituent components, revealed the presence of organic molecules alongside the methane. This was a critical finding, indicating that the methane wasn't just a simple atmospheric phenomenon, but potentially linked to more complex chemical processes. The problem was, the methane concentrations were incredibly variable. Some days, the levels would spike dramatically, only to return to near zero within a few days. This fluctuating behavior led scientists to consider several possibilities. One hypothesis suggested geological sources, specifically serpentinization. This process involves water reacting with magnesium-rich rocks, producing methane as a byproduct. Mars has abundant magnesium-rich rocks, particularly in its ancient crust. The circulation of shallow groundwater could, in theory, drive serpentinization, creating localized methane emissions. Evidence supporting this theory came from detailed mineralogical analysis of rocks near the Gale crater, where Curiosity is exploring. The presence of hydrated magnesium silicate minerals, alongside the detection of methane, strengthened the connection to this geological pathway. Another possibility involved subsurface reservoirs of methane trapped beneath the Martian surface. Microbes, similar to those found in Earth's permafrost, could be producing methane as a waste product of their metabolic processes. These microbes could be living in aquifers or within fractured rock formations, and their methane could be slowly released into the atmosphere. This scenario aligns with the possibility of extant life on Mars, though it's crucial to emphasize that this is purely speculative at this point. The challenge here is detecting these subsurface reservoirs, which would require drilling deep beneath the surface, a capability currently beyond the rover's instruments. The fluctuating methane levels also hinted at a potential connection to seasonal changes. The warmer Martian summers lead to sublimation of the dry ice polar caps, exposing more carbon dioxide to the atmosphere. This could influence the serpentinization process, changing the availability of water and, consequently, the methane production. Conversely, the colder Martian winters would suppress these reactions, reducing methane concentrations. Furthermore, dust storms, which are common on Mars, could play a role. Dust particles can absorb solar radiation, warming the surface and potentially stimulating chemical reactions. The search for a definitive source of methane continues, and scientists are employing a variety of techniques. Orbiters like the Trace Gas Orbiter, TGO, are providing global measurements of methane concentrations, helping to identify regions with elevated levels. The rover instruments are being continually refined to improve their sensitivity and to detect trace amounts of methane. Models are being developed to simulate the complex interactions between the atmosphere, the surface, and any potential subsurface reservoirs. Perhaps the most compelling argument comes from the analysis of the Gale crater itself. The crater is thought to have once been a lake, and the sediments deposited within it contain a remarkable diversity of organic molecules, far beyond what could be explained by purely abiotic processes, non-biological chemical reactions. While these molecules don't necessarily prove the existence of life, their presence dramatically increases the probability. The key is that the methane detected is often found in areas associated with these sedimentary deposits, suggesting a connection between the organic material and the gas. It's important to remember that the Martian atmosphere is a dynamic system, constantly influenced by solar radiation, seasonal changes, and potentially biological activity. Deciphering the origins of methane is a complex puzzle, and it's likely that multiple factors are contributing to its fluctuations. The ongoing exploration of Mars, with its sophisticated instruments and ambitious missions, is gradually shedding light on this mystery, bringing us closer to understanding the planet's past, its present, and perhaps its future. The search for answers isn't just about methane. It's about unlocking the secrets of a planet that has captivated scientists and dreamers for centuries. The surface of Mars, a rusty red ocean under a salmon-colored sky, holds secrets far older and more profound than the footprints of rovers. While we've been captivated by the search for water and the possibility of life, a silent, invisible force has shaped the planet's history in ways we're only beginning to understand. Mars' magnetic field. It wasn't always a void, a place where the solar wind relentlessly batters the atmosphere. Billions of years ago, Mars possessed a global magnetic field, a powerful shield protecting its early environment, and a key reason why its atmosphere, though now fragile, exists at all. The prevailing theory suggests that Mars was once a volcanically active, geologically young planet, much like Earth was in its youth. Intense planetary formation often involves a molten interior, and Mars certainly experienced that. This molten rock, rich in iron, created a swirling, electrically conductive dynamo within the planet's core. Just as Earth's rotation drives our magnetic field, this churning, metallic liquid generated powerful electric currents. These currents, in turn, created a magnetic field extending far out into space. This field acted as a barrier, deflecting the flow of charged particles, primarily electrons and protons, constantly emitted by the sun, a phenomenon known as the solar wind. The solar wind is a stream of particles traveling at incredible speeds, carrying with it a tremendous amount of energy. Without a magnetic field to intercept it, the solar wind would have directly stripped away the atmosphere of early Mars. These charged particles, if unimpeded, would have relentlessly eroded the atmosphere, pushing molecules, primarily carbon dioxide, outwards into the vacuum of space. It's a remarkably efficient process, and even a relatively small atmospheric pressure could have been completely obliterated over geological timescales. The existence of an atmosphere on Mars today is, therefore, fundamentally linked to the planet's past magnetic protection. Evidence for this ancient magnetic field comes from several intriguing sources. Scientists have identified regions on Mars, known as crustal magnetization sites, where the magnetic signature of the planet's interior is directly imprinted onto the planet's crust. These sites show distinct alignments of magnetic minerals, a predominantly magnetite and hematite, within the rocks. These minerals are particularly effective at retaining magnetism and provide a tangible record of the orientation of the magnetic field at the time they formed. The patterns of magnetization aren't random. They reveal the direction and strength of the field during specific geological periods. However, the most compelling evidence comes from observations of the planet's crust itself. Vast sheets of volcanic basalt formed during Mars' intense volcanic activity are also magnetized. These magnetized basalt formations are remarkably widespread, indicating that the magnetic field was pervasive and robust enough to influence the crystallization of these rocks as they cooled. The degree of magnetization within these rocks is directly correlated with the strength of the magnetic field at the time of their formation, offering a detailed timeline of the field's evolution. The crucial question then becomes, when did this global magnetic field disappear? The current best estimates suggest that the field began to weaken around 4 billion years ago. This wasn't a sudden event, it was a gradual decline. As Mars cooled, the movement within the core slowed and the dynamo became less efficient. The solar wind, relentless in its efforts to erode the atmosphere, began to penetrate the weakened magnetic shield. The loss of the global magnetic field had profound consequences. Without the protection of a strong field, the solar wind began to systematically strip away the atmosphere. Initially, this process was relatively slow, but over billions of years, the cumulative effect was devastating. The atmosphere thinned dramatically, particularly at the equator, where the solar wind's influence was strongest. The upper atmosphere, more vulnerable to solar wind erosion, was lost entirely. Interestingly, Mars still retains localized magnetic anomalies. These are smaller, weaker magnetic fields, remnants of a more complex, fragmented magnetic system that persisted for a longer period. These anomalies are often associated with regions of intense crustal magnetization, suggesting that the core's dynamo activity wasn't completely extinguished immediately. They represent pockets of lingering magnetic influence, a ghostly echo of Mars' former self. The absence of a global magnetic field significantly altered the planet's surface environment. Without the deflection of the solar wind, the surface was exposed to harmful radiation from the sun and cosmic rays. This increased radiation contributed to the breakdown of water molecules into hydrogen and oxygen, processes that would have been far more pronounced with a protective magnetic field. The hydrogen, being the lightest element, readily escaped into space, further diminishing the planet's atmosphere and water reserves. Currently, Mars' magnetic field is extremely weak, essentially a faint whisper compared to Earth's powerful shield. This weak magnetic field provides only limited protection against the solar wind, primarily concentrating around the polar regions. It's a poignant reminder of a planetary transformation, a story etched in the rocks and the thin, struggling atmosphere of the red planet. Understanding Mars' magnetic history is not just about reconstructing the planet's past. It's about understanding the delicate balance between planetary formation, atmospheric evolution, and the constant interaction with the solar wind. A lesson that could hold clues to the long-term habitability of other planets in our solar system. The Perseverance rover, diligently traversing the Jezero crater floor, isn't just searching for signs of ancient microbial life. It's also a tiny, incredibly sophisticated experiment in the future of space exploration, a test of how we might actually live on Mars. The grand ambition isn't simply to visit, it's to establish a sustainable presence, and a crucial element of that ambition lies in a concept known as in situ resource utilization, or ISRU. This essentially means using the materials already available on Mars to create what we need, rather than shipping everything from Earth, a tremendously expensive and logistically challenging undertaking. Initially, the concept might seem almost too simple. We're talking about taking a planet that, for the most part, appears barren and desolate, and transforming it into a source of fuel, water, and building materials. But Mars possesses resources, albeit in sometimes difficult-to-access forms. The first, and perhaps most immediate, focus is on water. The discovery of substantial water ice deposits near the equator, as explored in recent investigations, is not just a scientific find, it's a potential lifeline. That ice, concentrated within the crater floors and potentially accessible beneath the surface, represents a vast reservoir of hydrogen and oxygen, the key ingredients for rocket propellant. Creating propellant on Mars would dramatically reduce the cost of launching missions back to Earth or onward to other destinations within the solar system. The immediate plan involves developing technologies to extract this water ice. Perseverance carries a compact water extraction system, a small prototype designed to demonstrate the feasibility of melting and collecting the ice. This isn't about producing huge quantities of water at once. Rather, it's about proving the fundamental process works and understanding the specific conditions necessary for optimal extraction. The extracted water can then be processed into hydrogen and oxygen, the fuel that could power a Mars-based launch system. Scientists are also investigating methods of extracting water from hydrated minerals, clay deposits, and even the thin atmosphere, though this is generally considered a less efficient process. Beyond propellant, Mars' atmosphere, dominated by carbon dioxide, offers another avenue for resource utilization. While directly breathing the Martian air is obviously impossible, the carbon dioxide can be processed to produce methane, another valuable fuel source, and importantly, oxygen. This process, known as the Sabatier reaction, involves combining the carbon dioxide with hydrogen, which can be produced from the water ice, to generate methane and water. The water, of course, can be recycled back into the process. The efficiency of this reaction depends heavily on the availability of hydrogen, reinforcing the importance of the water ice discoveries. Another, longer-term, goal involves utilizing Martian regolith, the loose, rocky material that covers the planet's surface. This regolith is rich in minerals, including iron, aluminum, silicon, and titanium. With the right technology, these materials could be used to 3D print habitats, tools, and even building materials for a permanent settlement. Imagine constructing a shelter using Martian soil, fused together and strengthened with locally sourced minerals. This process, known as additive manufacturing or 3D printing, is already being tested on Earth, and adapting it to the Martian environment represents a significant step towards self-sufficiency. The challenges, however, are considerable. The Martian atmosphere is extremely thin, presenting difficulties for large-scale operations. Dust storms, common on Mars, pose a significant threat to equipment and solar power generation. The extreme cold temperatures add to the complexity of material processing. Furthermore, the regolith contains perchlorates, highly corrosive salts, which require careful management and potentially specialized filtration systems. Researchers are exploring various methods for overcoming these obstacles. Robotic systems, operating autonomously, would be crucial for long-term ISRU operations. Closed-loop systems, minimizing waste and maximizing resource recycling, are essential for sustainability. Scientists are investigating the use of Martian sunlight for energy generation and the potential for creating artificial habitats shielded from the harsh environment. The development of ISRU technologies is intertwined with the construction of a Martian base. The initial structures would likely be prefabricated, but the ability to utilize Martian materials for expansion and repair would dramatically reduce the reliance on Earth-based supplies. It's a concept that extends far beyond simply producing fuel. It's about transforming the very nature of our presence on Mars, shifting from a temporary visit to a more permanent and, ultimately, independent existence. The success of ISRU will fundamentally determine whether humanity can truly call Mars home. The next generation of missions will undoubtedly prioritize these resource utilization technologies, laying the groundwork for a truly sustainable Martian future. The Perseverance rover, a sophisticated explorer equipped with an incredible suite of instruments, isn't just collecting rocks. It's on a far more delicate and ambitious mission, searching for evidence that Mars might once have harbored life, or perhaps even still does in shielded, subsurface environments. This isn't about finding little green men. It's about identifying subtle clues, chemical or physical signatures, that could indicate the past presence of microbial organisms. These biosignatures, as scientists call them, are the traces left behind by living things, and their detection is a profoundly complex undertaking. The primary approach currently being employed focuses on the analysis of sedimentary rocks, particularly those found in the Jezero crater. This crater is believed to have once been a lake, a much more hospitable environment than the desolate, windswept plains we see today. Within these ancient lakebed deposits, scientists are looking for specific organic molecules. Organic molecules, such as methane and ethane, are the building blocks of life as we know it: carbon chains, proteins, and lipids. However, crucially, these molecules can also be created through non-biological processes, like geological reactions involving water and volcanic gases. Therefore, simply finding organic molecules wouldn't definitively prove life existed. Instead, the team is looking for patterns and ratios of organic molecules that are highly suggestive of biological origin. For instance, the discovery of complex, branched organic molecules, like certain lipids, in a specific geological context, perhaps alongside minerals that promote microbial growth, would be a significant indicator. The SHERLOC, scanning habitable environments with Raman and luminescence for organics and chemicals, instrument on Perseverance is central to this endeavor. SHERLOC utilizes a laser spectrometer to analyze the chemical composition of rocks at a very fine scale, mapping the distribution of organic molecules and identifying their types. The laser vaporizes tiny portions of the rock, and the resulting plasma is then studied to determine what elements and compounds are present. Another crucial aspect of the search is the investigation of mineral structures. Microorganisms often thrive in environments rich in certain minerals, and the presence of these minerals, along with associated organic molecules, can serve as a strong biosignature. Specifically, the team is interested in identifying minerals like carbonates and clays, which have the ability to preserve organic material over billions of years. These minerals can act like tiny vaults, protecting delicate organic compounds from being broken down by radiation or chemical reactions. Furthermore, the way these minerals form, through biological processes, for example, the precipitation of calcium carbonate by microbes, can provide evidence of their involvement. The Ingenuity helicopter, a technological marvel in itself, plays an unexpectedly important role in this hunt. While primarily designed to assess the Martian atmosphere and provide aerial reconnaissance for Perseverance, Ingenuity's high-resolution images are being used to identify areas with particularly interesting geological features: layered sedimentary rocks, fractures, and contact zones between different rock types. These features could represent locations where organic material might have been concentrated or preserved. Moreover, if Ingenuity can map the distribution of certain minerals, that information can be used to guide Perseverance's sampling efforts. Beyond organic molecules and mineral structures, scientists are also investigating the potential for detecting isotopic anomalies. Living organisms preferentially use certain isotopes, variations of elements with different numbers of neutrons, during metabolic processes. If microbial life once existed on Mars, it's possible that the ratios of these isotopes in certain rocks would be different from what we'd expect to find through purely geological processes. This is a far more challenging approach, requiring extremely precise measurements and sophisticated modeling to separate the influence of biological activity from other geochemical processes. The collected samples, carefully sealed in titanium tubes, represent the next vital step. Perseverance's mission isn't just about finding biosignatures. It's about caching these samples for a future sample return mission, slated to bring them back to Earth for far more detailed analysis in state-of-the-art laboratories. These laboratories will be equipped with instruments far more powerful than anything currently deployed on Mars, allowing scientists to perform techniques like mass spectrometry and detailed microscopy, techniques that could potentially reveal the very existence of fossilized microbial remains, or perhaps even detect traces of DNA or RNA. It's important to acknowledge that detecting biosignatures on Mars is an incredibly difficult task. Mars has been exposed to intense radiation over billions of years, and its surface environment is harsh and unforgiving. Any evidence of past life would likely be heavily degraded. However, the combination of Perseverance's instruments, Ingenuity's aerial observations, and the eventual return of the cached samples offers the best chance yet of answering one of humanity's oldest and most profound questions. Are we alone in the universe? The search for these subtle, yet potentially transformative, clues is a testament to human curiosity and our unwavering desire to understand our place in the cosmos. It's a patient endeavor, demanding meticulous investigation and open-minded interpretation, and it holds the possibility of rewriting the history of our solar system. The red dust of Mars has held secrets for billions of years, and scientists are painstakingly working to unlock them, particularly concerning the planet's climate. It's not simply about whether Mars is cold today. The real puzzle lies in understanding how its climate has shifted dramatically over vast stretches of time, and what might happen as we consider longer-term human presence. The early models relied heavily on Earth's experience as a guide, but the stark differences between the two planets, especially the lack of a global magnetic field, introduced significant complexities. Early simulations suggested a relatively stable, albeit cold, climate for much of Mars' history. This was based on the assumption that the weak solar wind bombardment, lacking a protective magnetic field, couldn't easily strip away the atmosphere. However, as data from the Curiosity and Perseverance rovers accumulated, particularly evidence of ancient lake beds and river systems, scientists realized that Mars had experienced periods of considerably warmer temperatures and a thicker atmosphere. The key to unlocking these past climates rests largely on analyzing the chemical composition of Martian rocks and soils. Instruments on the rovers, like the Sample Analysis at Mars, SAM, Suite on Curiosity, and the SHERLOC spectrometer on Perseverance, are meticulously examining the abundance of elements like sulfur, chlorine, and magnesium. These elements are particularly sensitive to temperature variations. High temperatures tend to liberate them from rocks, and their concentrations in the soil act as a kind of geological thermometer, allowing scientists to reconstruct past temperatures with increasing precision. For example, the discovery of hydrated silica, a mineral that only forms when water is present and at relatively warm temperatures, within the Gale crater, where Curiosity has been exploring, provides strong evidence for a warmer, wetter past, perhaps around 3.7 billion years ago. What's even more intriguing is the identification of features suggestive of vast, shallow seas. The presence of carbonates, minerals which form in water-rich environments, and the layered sedimentary rocks within these ancient basins strongly suggest that Mars was once covered by a much more extensive ocean than we currently believe. Modeling these periods requires sophisticated computer simulations that account for the influence of the solar wind, the planet's rotation, and the albedo reflectivity of the surface. Albedo is crucial because it determines how much sunlight is absorbed versus reflected. A darker surface absorbs more sunlight, leading to warmer temperatures, while a brighter surface reflects more sunlight, keeping things cooler. The absence of a global magnetic field is, of course, central to all of this. Without it, the solar wind, a constant stream of charged particles from the sun, relentlessly eroded the Martian atmosphere. This process, known as sputtering, strips away atmospheric gases, and because Mars has very few heavy elements in its crust, the lighter gases like carbon dioxide and water vapor were especially vulnerable. The impact of this erosion is profound. It drastically reduced the atmosphere's ability to retain heat and led to a gradual decrease in temperature over billions of years. However, current models are beginning to incorporate a more nuanced understanding of this atmospheric loss. Scientists are now exploring the possibility that the solar wind didn't act uniformly across the planet. There's growing evidence suggesting that the upper atmosphere might have been more shielded from direct solar bombardment due to interactions with the tenuous, ionized plasma surrounding Mars. This creates a complex, layered atmosphere where different processes are at play. Looking ahead, the most pressing questions revolve around projecting the future climate of Mars, particularly in the context of human colonization. Even with efforts to terraform, transforming Mars to resemble Earth, the planet's inherent challenges remain. Any significant warming would be difficult to control because, again, there is no global magnetic field to deflect the solar wind. Furthermore, the lack of a substantial atmosphere means that any changes in albedo, such as deploying large reflective mirrors to increase sunlight absorption, would have a disproportionately large impact. Scientists are building models to explore various terraforming scenarios. One approach involves releasing massive amounts of carbon dioxide into the atmosphere, initially via the deliberate fracturing of Martian rocks. This would thicken the atmosphere and trap more heat. Another, more radical idea involves creating an artificial magnetosphere, perhaps through a network of orbiting satellites, to deflect the solar wind. These models aren't just theoretical exercises. They are vital for informing the design of habitats, the selection of plant species for potential food production, and the overall strategy for establishing a sustainable human presence. The simulations are constantly refining as new data comes in. The latest observations from Perseverance, for example, are refining our understanding of the ancient Martian environment and providing crucial input for future climate models. The challenge isn't just about predicting the temperature. It's about understanding the intricate interplay between atmospheric processes, surface geology, and the solar wind, a system that has been evolving for billions of years and will continue to shape the fate of Mars for millennia to come. The future of humanity on Mars depends, in part, on fully deciphering this ancient, dynamic story. The reddish dust of Mars has, over billions of years, been shedding pieces, tiny fragments of the planet itself. These aren't just random rocks, they're Martian meteorites, and their discovery and study have become an unexpectedly vital window into understanding the red planet. The initial finds, made in Antarctica during the 1960s, were truly startling. These weren't just rocks that had traveled through space. They were demonstrably Martian material, possessing a unique composition and a distinctly different history than anything found on Earth. The first, designated ALH 8401, was a particularly intriguing find, a small, porous stone that showed evidence of aqueous alteration, suggesting it had been exposed to liquid water at some point. This immediately raised the question: had water ever played a significant role in shaping Mars? The story of Martian meteorites doesn't begin with the spectacular discoveries of the 1960s, however. It's a narrative that stretches back much further, rooted in the meticulous examination of terrestrial rocks. Scientists realized that studying rocks formed in environments similar to those believed to have existed on Mars, environments rich in water and volcanic activity, could provide incredibly valuable insights. Specifically, they turned their attention to iron formations, those striking bands of rich iron oxides that dominate the landscapes of places like the Canadian Shield and the Pilbara region of Western Australia. These formations, sculpted by ancient, shallow seas and hydrothermal systems, provided a terrestrial analog to the putative aqueous alteration seen in some Martian meteorites. The Pilbara region, in particular, emerged as a crucial point of comparison. It's a geologically complex area, characterized by extensive hydrothermal systems and ancient sedimentary rocks. Scientists found that the mineral assemblages, the specific combinations of minerals, within the Pilbara rocks mirrored those found in some Martian meteorites, notably in the Muriates, a group of meteorites that are considered the most closely related to the Martian surface. These meteorites contain minerals like smectite clays, serpentine, and magnetite, all of which are formed through reactions between water and rock. The presence of these minerals wasn't just a coincidence. It demonstrated that similar chemical processes, the alteration of rock by water, could occur on Mars, just as they did in the Pilbara. The study of these terrestrial analogs wasn't just about identifying similarities. It was about understanding the processes involved. Scientists could recreate, in laboratory settings, the conditions believed to have existed on Mars, simulating the interaction of water with Martian rocks. They could then analyze the resulting mineral changes, meticulously documenting the formation of clays, the oxidation of iron, and the precipitation of various minerals. These experiments helped refine models of Martian geology, providing a framework for interpreting the data gleaned from Martian meteorites. For example, research showed that the specific types of clays found in some meteorites could be produced by recreating the conditions of shallow, acidic groundwater systems, a plausible scenario for Martian aqueous environments. Furthermore, the study of terrestrial iron formations, such as those found in Greenland, offered another vital perspective. These formations, which often contain high concentrations of magnetite, are believed to have formed through the precipitation of iron minerals from hydrothermal fluids. The characteristics of these terrestrial magnetite deposits provided clues about the potential magnetic field of ancient Mars. The strength and direction of the magnetic field are incredibly important because they can tell us about the planet's interior structure and how its magnetic field interacted with the solar wind, a constant stream of charged particles from the sun. The study of terrestrial magnetite helped constrain the models being developed for the Martian magnetic field. The analysis of Martian meteorites, combined with the insights gained from these terrestrial analogs, has gradually built a detailed picture of Mars's early history. It suggests that Mars was once a much warmer, wetter place, with abundant liquid water circulating beneath the surface. This water likely played a crucial role in shaping the planet's landscape, creating vast lake beds, river systems, and potentially hydrothermal vents, environments where life could have conceivably emerged. The study of these meteorites isn't about finding definitive proof of life on Mars, but rather, it's about understanding the conditions that could have supported life. The data coming from Martian meteorites is complex, requiring sophisticated analytical techniques such as electron microscopy, mass spectrometry, and isotope analysis. These methods allow scientists to examine the tiny details of the meteorite's composition, searching for signatures of past aqueous activity, volcanic processes, and even potential biosignatures, chemical traces that could indicate the presence of microbial life. It's a painstaking process, but every new discovery, every new piece of information, brings us closer to unlocking the secrets of the Red Planet. The ongoing study of these remarkable rocks continues to reshape our understanding of Mars's past, and with each finding, the possibility of discovering life, either past or present, becomes a little more compelling. The rovers, Perseverance and Ingenuity, had already carved their own stories across the surface of Mars, meticulously examining the slopes of the Jezero crater, once a lakebed brimming with potential secrets. But Mars held an even grander, more profound mystery, a chasm so vast, so complex, that it dwarfed even the most ambitious terrestrial canyons. This was Valles Marineris, a system of canyons stretching over 4,000 kilometers across the planet, dwarfing the Grand Canyon of Earth in both length and depth. The initial data gathered by orbiters, the Mars Reconnaissance Orbiter and the Mars Express, provided tantalizing glimpses, revealing layered rock formations and vast outflow channels, hinting at immense geological forces at play. However, a truly comprehensive understanding demanded a closer, more detailed look, and that's where the robotic mapping efforts began to truly ramp up. The core of this mapping operation centered on the Mars Descent Imager, MWI, carried aboard Ingenuity. This compact instrument wasn't designed for high-resolution photography like some of the other cameras. Instead, its purpose was to create detailed topographical maps in the near-infrared spectrum. The MWI could detect subtle differences in the mineral composition of the rocks, identifying clays, sulfates, and other materials which are particularly important because they often indicate past water activity. By analyzing how the light reflected from these materials, the MWI was able to build a 3D model of the canyon walls, layer by layer. It was like creating a geological time capsule, documenting the history of the region through the patterns of light and shadow. The initial data from Ingenuity focused on the Coprates Chasma, a particularly prominent section of the Valles Marineris system. The rover's flight path was carefully chosen to provide overlapping views, allowing scientists to stitch together a highly detailed map. The MWI wasn't just simply measuring elevation, it was discerning the type of rock as it rose and fell. The team discovered that the canyon walls in this area weren't uniformly composed. Instead, they found distinct layers, some rich in hydrated sulfates, others displaying evidence of fluvial processes, suggesting ancient streams had carved their way through the rock. The rover's ability to make these observations from its unique vantage point, skimming just above the canyon floor, was critical. It allowed the team to see features that were simply inaccessible to stationary landers. As Ingenuity's mission progressed, the mapping efforts expanded to include the Candor Chasma, another enormous section of the system. The MWI data revealed incredibly complex faulting and fracturing, evidence of massive tectonic movements that had shaped the canyons over billions of years. These faults weren't just simple breaks in the rock. They were often filled with younger volcanic materials, providing a record of repeated episodes of volcanic activity. Analyzing these fillings, the textures, the mineral content offered clues about the processes that had triggered these volcanic events. Furthermore, the data collected by Ingenuity was meticulously compared with radar data acquired by the Shallow Radar (SHORAD) instrument. SHORAD sends out radio waves that penetrate the Martian surface. By analyzing how these waves bounce back, scientists could map the subsurface geology, identifying buried valleys, sedimentary deposits, and even potential aquifers, reservoirs of water ice beneath the surface. The combination of MWI and SHORAD provided a truly three-dimensional understanding of the canyon system, far exceeding what could be achieved with either instrument alone. The sheer scale of the Valles Marineris presented unique challenges. The rover's limited range of vision and the difficulty of navigating the steep canyon walls demanded incredibly precise flight control. The team developed sophisticated algorithms to automatically plan Ingenuity's flight paths, taking into account the terrain, the lighting conditions, and the scientific objectives. Each flight was a carefully choreographed dance, with the rover hovering just above the canyon floor, collecting data and transmitting it back to Earth. The data collected was slowly building a picture of a region shaped by colossal floods, tectonic upheaval, and potentially periods of significantly warmer and wetter conditions than Mars currently experiences. The mapping wasn't just about creating pretty pictures. It was about understanding the history of water on Mars. The team hypothesized that the Valles Marineris might have formed in part due to the collapse of a vast, ancient crustal block following a period of intense volcanic activity. This hypothesis is supported by the layered structures observed in the canyon walls and the presence of sedimentary deposits that indicate the flow of water. As the mission continued, the potential for discovering evidence of past life in the Valles Marineris grew stronger. The canyon system provides a natural laboratory for studying ancient environments and the diverse range of geological features. The layered rock formations, the sedimentary deposits, and the potential for subsurface water ice increases the chances of finding evidence that life may have once existed on Mars. The robotic mapping efforts are laying the groundwork for future, more detailed investigations of this remarkable system, promising to unlock even more of Mars's secrets. The reddish dust of Mars settled softly on the northern plains, a landscape sculpted by ancient winds and long-gone rivers. But beyond that familiar vista, clinging stubbornly to the planet's poles, lay a secret: vast, frozen reservoirs of water. The Martian polar regions, particularly the north, held a surprising and crucial key to understanding Mars' past, and more tantalizingly, its potential for the future. Scientists realized that these weren't simply frozen water. They were complex ice caps, layered like giant, frozen time capsules. These layered deposits were primarily composed of water ice, mixed with dust and, surprisingly, other materials that offered clues about Mars' atmospheric history. The northern polar cap, known as Planum boreum, is a remarkable feature. It's not a single, solid sheet of ice like the ice caps of Antarctica or the Arctic. Instead, it's a series of coalescing, overlapping deposits formed over countless Martian years. These deposits, formed primarily during Mars' warmer periods, are incredibly dynamic. They expand and contract as the planet's climate fluctuates, influenced by its orbit around the Sun and the distant tug of Jupiter. The size of the northern cap dramatically varies. It can swell to nearly double its minimum extent during warmer periods, then shrink back down as the planet cools. This cyclical expansion and contraction creates a spectacular visual display, a shimmering white expanse against the rusty red of the surrounding landscape. What makes these ice caps so important isn't just the water ice itself, though that's a critical discovery. Embedded within the ice are grains of dust, minerals, and even tiny pebbles, material swept up from the Martian surface by the wind. These particles act like a record, preserving information about the composition of the atmosphere at different times in Mars' history. Scientists meticulously analyze the isotopic ratios of these trapped gases. By comparing these ratios to those found in meteorites and lunar samples, they're piecing together a detailed picture of Mars' early atmosphere, a period when it was likely much thicker and warmer than it is today. The presence of methane, a gas that can be produced by biological or geological processes, has also been detected within these ice layers, adding another layer of intrigue. The southern polar cap, known as Planum austral, is considerably smaller and more stable. Unlike the dynamic northern cap, it is largely composed of water ice and exhibits less seasonal change. Its stability makes it an ideal location for robotic exploration. The Mars Reconnaissance Orbiter's high-rise camera has provided stunning close-up images of the southern ice cap, revealing features like layered deposits, dark streaks, and even the presence of boulders frozen within the ice. Scientists are particularly interested in studying the interactions between the ice and the surrounding bedrock, seeking evidence of past water flows and potential subsurface aquifers. The investigation of the southern ice cap isn't just about understanding Mars' past. It's also about considering the possibility of present-day habitats. Subsurface water ice, even if it's frozen, could potentially be accessed and utilized by future human explorers. The idea is that beneath the surface, where it's shielded from the harsh radiation and extreme temperature fluctuations of the Martian environment, liquid water might exist. This liquid water could provide a source of drinking water, oxygen, and perhaps even a stable environment for growing food. Several missions are planned to directly investigate the subsurface ice at the South Pole. The Rosalind Franklin rover, part of the European-Russian ExoMars program, is equipped with a radar instrument called RIMFAX, designed to penetrate the ground and map the subsurface structure. The data collected by RIMFAX will help scientists identify potential aquifers and assess the accessibility of the ice. Other missions, including potential robotic drilling projects, are being considered to directly sample the subsurface ice and analyze its composition. The exploration of the Martian polar regions represents a crucial step in humanity's quest to understand and potentially inhabit another world. These icy landscapes hold the secrets of Mars, climate evolution, and potentially the building blocks for a sustainable future. The ongoing robotic investigations, coupled with increasingly sophisticated analytical techniques, are steadily unveiling the complexities of these frozen worlds, inching us closer to answering the fundamental question: was Mars once a habitable planet? And perhaps more importantly, could it be again? The data emerging from the polar regions is not just about science. It's a story of resilience, of change, and ultimately, of hope. The hope that we can learn from the past and build a brighter future, even on a planet as distant and challenging as Mars. Further exploration of these icy domains promises to reshape our understanding of the solar system and our place within it. The journey to Mars is a profoundly delicate undertaking, a quest fraught not just with technical challenges, but with a deep, inherent responsibility. Before we even consider setting foot on the red planet or sending a rover to roll across its dusty surface, we must grapple with a concept called planetary protection. This isn't about building walls or barring entry. It's about safeguarding Mars itself, and also safeguarding our understanding of it. We have to consider the possibility, however slim, that we might inadvertently introduce earthly microbes, organisms that have evolved here on Earth, to a world that may, or may not, harbor its own native life. The core worry is contamination, the introduction of foreign life forms, whether benign or harmful, that could compromise the search for Martian biology. It begins with the simple fact that we are already teeming with microbes. Every human being, every piece of equipment launched from Earth, every single drop of fuel contains a vast and incredibly diverse collection of microorganisms. Some are helpful, some are harmful, but they are undeniably there. These microbes have adapted to thrive in a stunning array of environments here on Earth, and it's impossible to guarantee they wouldn't also survive on Mars. The Martian environment, while different, isn't necessarily sterile. Subsurface environments, for example, might offer conditions that could support microbial life, and we wouldn't want to disrupt that potential. The protocols are layered and incredibly strict, designed to minimize the risk at every stage. It starts with the design and construction of spacecraft. Materials used must be carefully chosen, largely inert substances like titanium and Teflon, to avoid introducing materials that could support microbial growth. Electronics are shielded to reduce potential contamination. Even the paint used on spacecraft is scrutinized. Some paints contain additives that could promote microbial growth. Then there's the preparation of the astronauts themselves. Before launch, astronauts undergo extensive quarantine periods, often lasting months in specialized facilities. They are meticulously monitored for signs of microbial shedding. Their clothing, equipment, and even their waste are treated to reduce the number of microbes they carry. It's a demanding process, designed to minimize the biological passport each astronaut carries. But spacecraft aren't the only objects requiring protection. Every component sent to Mars, rovers, landers, instruments, undergoes a similar sterilization process. Robotic probes are rigorously cleaned and sealed to prevent the escape of microbes. The challenge is finding the right balance. We need to sterilize these objects effectively, but we also don't want to damage delicate scientific instruments. Superheating, using high-pressure steam, and even exposure to radiation are all employed, each with its own set of potential drawbacks. Once a mission is nearing Mars, a decontamination phase is initiated. This involves further cleaning and sealing of the spacecraft, often using chemical treatments to reduce microbial populations. The goal is to significantly reduce the number of microbes, although complete eradication is impossible. The spacecraft is then placed in a clean room environment for a period of time, allowing any remaining microbes to settle and be removed. Even after landing, protocols remain in place. Rovers, for instance, are designed with features to prevent the spread of contamination. Wheels are treated to minimize the transfer of soil, and instruments are designed to operate in a way that reduces the risk of soil disturbance. Strict protocols govern the collection and analysis of Martian samples. This is arguably the most sensitive area of planetary protection. Any sample returned to Earth would be treated as a potential biological hazard, requiring a dedicated facility for safe handling and analysis. The planetary protection framework isn't just about preventing contamination. It's about ensuring the integrity of our scientific investigations. If we were to inadvertently introduce terrestrial microbes, our conclusions about Martian life, whether it exists or not, would be fundamentally compromised. It would be like trying to diagnose a disease with a contaminated sample. The challenge is immense, a constant balancing act between scientific ambition and the ethical responsibility to preserve the potential for discovering truly native Martian life. There are ongoing debates and refinements to these protocols as we learn more about Mars. For example, the possibility of subsurface liquid water and the potential for extant life in these environments increases the scrutiny surrounding any exploration activities. New technologies, such as advanced sterilization methods and containment systems, are constantly being developed and tested. The entire process is a testament to our careful consideration of the broader implications of space exploration. It represents a deep respect for the unknown, a willingness to proceed cautiously, and a commitment to safeguarding a potentially remarkable world. Ultimately, planetary protection isn't a barrier to exploration. It's the foundation upon which responsible and meaningful Martian science can be built. As the rovers rest upon the red dust, let the images of Mars gently fade within your mind. This journey through the canyons and craters has ended for now, a quiet echo in the vastness of space. Allow your thoughts to drift, soft and unhurried, like the distant stars. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Allow your thoughts to drift, soft and unhurried like the distant stars.